Okay, hello everyone. Good evening. How are you doing? Yeah, we'll just wait for a few more minutes. People are just joining in. Yeah. Okay, good evening everyone. Let's get started with the live session. So, uh, any general comments on week 7? Uh, did you get a chance to go through the videos? Uh, any concerns? Yeah. Anything you all want to share? Were you all able to go through the videos? Okay, no response.
So still in week 6 only. Haven't watched the week 7 lectures. Yes.
Hmm. Okay. So I think most of you haven't started week 7, no? Okay. Let's see what we can do in this session then. Okay. All right. Let's maybe start with yeah, let's start with some activities then. I'll just share something here. Okay, hope you all can see the link which I shared with you on the chat. See if you can open it. Okay, let me start sharing my screen. All right. All right. So let's get started. What you can do is either go to the link which I shared in the chat, or you can, yeah, go to menti.com and use this code 17975038. Go to menti.com and use the code 17975038. I'll just wait for a few more
One
minutes.
seven nine seven 503.
Okay, so yeah, the first question is, yeah, how many lectures have you viewed till now? In okay, either it's all the lectures or none of the lectures. Okay, yeah, only seven, eight responses. Yeah, I want all of you to log into menti.com and type in this code 17975038. Share the link here also.
Sir, will you discuss the Hoffman coding today?
Huffman coding, I can. Yes, I will. So my plan is to discuss the AVL trees and Huffman coding. Yeah.
Okay. And so actually Hoffman coding, it's I understood that thing, but only thing to get the means generation of this binary sequence means zero one
Mhm.
zero one, that when we are from the bottom to generate that binary, that part in coding I am facing some problem.
Okay, okay. Sure, sure. Let's discuss that. Maybe towards the end we can discuss that. Yeah,
Okay.
because many might not still be aware of what Huffman coding is. I'll give a brief introduction and then we can discuss that, right?
Okay.
Yeah. Okay, any more responses? So 33 have joined and only 14 have responded. Others, you can please go to menti.com and use this code 17975038, or you can use this link. All right, so it seems that a majority of you haven't watched the lectures, right? So yeah, so I think I will go through some of the concepts in this week, and hopefully by tomorrow or by Saturday you'll have some more doubts or some clarifications which you need. So okay, sure. So if this is the case, then yeah. So which concepts are you finding difficult? Okay, let's not restrict to week seven then. Let's go to week six and week five also. Those who have done week seven, you can respond for the concepts which you're finding difficult in week seven. Uh, but I think others you are free to mention things in week five and six also. Okay, any more responses? You can think about week six and week five also, if anything is coming to your mind. Okay, week five, Floyd Warshall. Any more responses? Okay, binary tree. Okay, so I can see week 5 some things about Floyd-Warshall. Uh, yeah, Floyd-Warshall is yeah, two of you have responded that and responded to that. Okay, if I focus on week 7, yeah, so week 7 is focusing on greedy algorithms, right? And what greedy algorithms are is that in order to solve the entire problem, you start off, you make a decision, a very local decision, uh, and you continue doing that till the entire problem is solved, right? And so in week 5 and 6, you all saw uh, algorithms like the Dijkstra's algorithm or the Prim's algorithm, where, for example, in Dijkstra's, from the source node, you selected the shortest distance edge first. And then again, you continue doing that till you reach the destination, till you reach all the other nodes, right? So that local decision, that local decision at every point leads to the final solution. And if you watch the lectures, many a times uh, we really do not know, what criteria to choose or what aspect we should actually choose a particular step, right? In which aspect should you be greedy? So the lectures have different scenarios where sir talks about, some greedy algorithms work, some criteria work, but some do not work. So you can go through the lectures to understand that part. And some of you have one of you have said about AVL trees and binary tree, AVL tree size, right? Okay. Yeah. And yeah, even in this week and the previous weeks, yeah, I agree that maybe the some of the coding part has not been explicitly mentioned, but I think the purpose of that and the assignments and all of that is for you to uh, having no having got these concepts, I think you can go about implementing them, right? I think even in this week, right, week 7, you will see that sir explains the main algorithm, the crux of the algorithms, and in the assignments and the practice assignments, programming assignments, you will go about implementing, right? So, yeah, coding, I think through I would encourage all of you all to watch the lectures. Maybe just watch the first few lectures. Or maybe just watch one topic and then think of how you can implement that algorithm, right? Take an editor and start coding. And some of the practice assignments also actually talk about implementing those algorithms. So rather than watching all the videos first and then going to the assignments, I would suggest you all start watching one video, think of coding up that algorithm, or go to the practice assignments to see if there is that algorithm, that problem, and try attempting that, right? So in that way, I think you will be able to uh, start working on the coding part, and hopefully that will help you in, yeah, coding the algorithms. All right. So then what I'll do now is, yeah, so uh, today's live session, I'm thinking of talking about AVL trees and going through some problems in AVL trees and uh, also look at Huffman coding. Okay, that is one algorithm which was explained in week 7. Okay, so Okay, so this is a question which I have for you all. You all remember binary trees, right? We learned it in the previous week. So if you all remember what a binary tree is, so let's take an example of uh, oops. Yeah, let's take an example of, let's say, uh, 4, 4, and anything to the left of a node is lesser than that. Anything to the right of that is greater than that, right? So this is a binary tree, right? So this can be 1, this can be, yeah, something like that. So this is a binary tree, right? So the question is, uh, which of the following inserts? So assume 5 is inserted first, followed by 4, followed by 3, followed by 2, followed by 1. This is one sequence. Another sequence is you insert 3, then followed by 2, followed by 4, followed by 1, followed by 5, right? So which of the following inserts to an empty binary tree will result in a tree with maximum height? So by height, I mean starting from the root up to the leaf, right? So in this case, the height, if you consider this as of height 1, this will be 2, this will be 3. So this tree has a height of 3, right? All right. So the question is, yeah, so I've given some options. Which of them do you think will result in a tree with a binary tree with the maximum height? Okay, many of you are telling the first option. One of you has said 2, 4, 1, 3, 5. Okay, someone is asking for Mentimeter link. Yeah, it's over here. Or you can go to menti.com and use the code 17975038. Okay, only 12 of you have responded. We have around 50 participants. Yeah, I would encourage all the others also to please join the Menti link. I've pasted it on the chat. And okay, so one of you have responded as 24135. Yeah, can you explain the reason why you think that is so? 2, 4, 1. Uh, is there any reasoning for 24135? Okay, so I see maximum of you have responded to 54321. Can one of you unmute and tell me why you think so?
Yes, sir.
Yeah, Priyadar, go ahead.
So basically, in a binary tree, the process is that while making the binary tree, the left side consists of all those nodes which are less than, and the right side are greater than the main root node. So
Okay,
when we go for arranging 5, 4, 3, 2, 1, basically the 5 becomes the root node, and when 4, since it is less than 5, so it will come to the left side. 3, since it is also less than 5 and less than 4, so it will also come to the left side. And similarly, all the rest 2 and 1 will also come to the left side.
right. And the height of this is
5.
5, right? So this is, if you consider this as 1, then this is 2, this is 3, this is 4, this is 5, which in a way is, so if the number of elements are n, the height of this tree is actually n. And what that means is, if you want to search for a particular element, let's say if you want to search for 5 in a binary tree of this form, instead of taking log n time, it is going to take n order of n, right? And that is the problem, right? And hence, that is the reason why we somehow need to balance these trees, right? So that it will, so that the height will reduce and the height will be in the order of log of n, right? And that is the reason why we do do something known as balancing, right? And such type of trees are known as avial trees. Hmm. So, as we said, a height is, if there is uh, if it's an empty tree, then its height is 0. If there is a tree only with only one root node, then the height is 1. And otherwise, the height is 1 plus max of the heights of the left and the right trees, right subtrees, right? So, for example, if we take 2, 4, 1, 3, 5, right? So 2, 4, 1, 3, this is 5 over here. So the way to think about it is, height of 3 is 1, height of 5 is 1, height of 4 is, can you all respond on the chat? What do you think the height of 4 will be? The height of 4 will be, can you respond on the chat? Height of 4, okay, 1, 2, 1, 2, getting some 2s, getting some 1s. So the height of node 4, okay, mix of 1s and 2s, right? So let's look at what the formula was. It is 1 plus max of heights of left and right subtrees. So 1 plus max of 1 plus max of left is 1, right is 1. So which is 1 plus 1, which is equal to 2, right? Similarly here, it doesn't have any children, so the height of 1 is 1. Then the height of 2 is 1 plus max of left, which is 1, and right, which is 2. And so it is 1 plus 2, which is equal to 3, right? So in short, the way to think about it is, height is from that root all the way up to the leaf, how many nodes are there in a way. So 1, 2, 3, right? Yeah. So that was height, right? All right. And to ensure that a tree is balanced, what we need to ensure is that the self dot left dot height, the self is the node. So for example, 2 is a node. Its left ka height and its right ka height should differ by at most 1. Such type of trees are known as abial trees, right? So this, in this case, do you think this is an abial tree? Can you reply on the chat, yes or no? This is an avial tree. Some of you are saying yes. Shamit is saying no. Okay, only if you have responded yes, no. Any more responses? Do you think this is an ABL tree? Okay, someone who has said yes, can you tell me why do you think so?
Yes, sir.
Yeah, go ahead.
So in a balance, basically balance ABL tree is such that the height of the left subtree and right subtree difference should be at most 1. It
Okay,
can be either 1 or 0. So in here we can see that in the right subtree, the height is 2, and in the left part of the subtree, the height is 1. So 2 minus 1 or 1 minus 2, basically at most is 1.
okay,
So hence it is
okay.
a balance.
All right. And someone said no, right? Who all thinks it's no? Can you?
Sir, I said no because in the graph, the
Ah,
node number two is unbalanced because the left hand side is 3, the right hand side is 1. So 3 minus 1 is 2. So node 2 is the 2. So that is why this graph is unbalanced.
oh, you're talking about this node too? This one?
Yes, yes, sir.
Why do you say it's unbalanced?
Because the left hand side it is 3 and the right hand side it is 2.
Left hand side is 3 as in? I didn't understand.
Oh, sorry. This is 1, 2. No. The balance. Sorry.
Okay, okay.
Sorry.
No issues. So intuitively, what you can see is if you know the left and the right do not differ by more than one level. That's another way about thinking of it. If you see two, see one is balanced, there's nothing below it. All the leaf nodes, there's no issue. Four, you can see it's balanced because the left and the right both have one child. Here, two, if you see the left, the left, uh, the left subtree and the right subtree differ by only one level, right? So if you see the height, okay, so these are the heights, right? So the height, if you look at this formula, left of height minus right of height should differ by only one. So this is one and this is two. So if you subtract one and two, yeah, if you take the mod, right, mod of this, it is one. So it is differing by only one. So in that case, we can say that a tree is balanced. Okay. So this thing of, okay. So, uh, yeah, I think I already gave the answer, but okay, I want you all to maybe in your notebook or something, draw this 2, 1, 4, 3, 5. And can you tell me the height of each node? What is the height of each node in the following binary tree? Yeah, so the answer is already there, but yeah, I want you all to just think about it and no responses.
So where to answer means Menti.
Yeah. Yeah, on Menti, on Menti. Okay, this is not giving the appropriate thing, but yeah, let's
Sir,
sorry about that.
here it is no value of 0.
Yeah, sorry. Yeah, we can skip that, sorry. So I think you all understood, right? The height is uh yeah. So the height is nothing but if it's a single node, the height is 1. Uh, and at each time it is 1 plus max of the left and the right trees ka height, right? So any doubt in this, right?
Sir, one question, just have a confusion.
Yeah.
If you say a single node is one,
Hmm.
then in the graph, this 2 1 4 3 5, this graph
Hmm.
in
Hmm.
the screen,
Hmm.
what is the height of the two? It is 3, right?
Yes, yes.
And so let,
See, it is a convention in a way, so you can even consider heights of these as zeros. Okay,
yes, that's
three
a
and five,
mm,
3 and 5 can be zero. The only, yeah, and then this will be one, this will be two. That's just a convention, which we have decided that, one will be for a tree with only one root node. So that's the convention we are following. It won't affect the ABL tree because you are subtracting the left and the right heights. So whether you start from zero or whether you start from one, the difference should be at most one. That's
yes,
the
yes.
that's the main.
Sir, had a query one.
Yeah, go ahead.
So basically, can we say that height of a particular node can be equal to 1 plus level of that node? Basically, node 2 is at level 0, so height is equal to 1 plus level of 2.
Yeah. In a recursive way, you're saying, right?
Yes, sir.
Yeah, sure.
Thank you, sir.
Yeah. All right. So if that is the case, yeah. And slope of a node, okay, is nothing but you take the height of the left subtree and subtract it from the height of the right subtree, right, for each node. So a balanced tree in a way is such that each node, the slope of each node will be either be 0, -1, or +1, right? Of a balanced tree, the slope will either be -1, 0, or 1, right? Remember, the slope is you take the left height of the left subtree subtracted from the height of the right subtree, right? Okay. So if that is the case, can you tell me what is the slope of node 2 in the binary tree, the same binary tree, 2 1 4 3 5? What is the slope of node 2 in the binary tree? 2 1 4 3 5. Okay, if you have not, I would encourage you all to just draw it on a sheet of paper or something. Okay, only 3 have responded till now. Yeah, I'm pasting the link again for the Menti. Okay, only 7 responses. Others, please respond. You want to see it? It is this. What is the slope of node 2? Okay, others, I'm waiting for your response. Only 11. Okay, so we have -2, 1, and -1 is the majority. Okay, so why -1? Can one of you respond?
Yes, sir.
Okay, other than Priyadash, someone else
Left
wants
minus
to?
right, sir. Height of left minus right. So left from
Okay.
is 1 and right is 2. So 1 minus 2.
Okay, so you're saying left minus right, right? So what is the slope of the left subtree? This one.
Mm. Yes.
Yeah, so what is the slope of the left subtree? Sorry, the height of the left subtree.
1,
Yeah, 1. And the height of the right subtree
2.
is 2. So 1 minus 2 is minus 1, right? I hope it's clear for others who responded minus 2 and 1. Any doubts regarding this? All right. Okay. All right. Good. Okay. So this was some basic things which I wanted to cover in this. So now what we need to see is what AVL trees does is, right? So for example, let's take an example of this only, 5, 4, 3, 2, 1, right? So what happens is AVL trees in a way try to rebalance when there is some imbalance, right? When the slope of any of the nodes become either +2 or -2. Uh, so there the possibilities can be when you insert something or when you delete something, this imbalance can happen, right? So for example, you have 5. When there's just one node, the slope is, there's no left, there's no right, so it's 0. Now if I add 4, right? So can you all tell me what is the slope of 5?
1.
Okay, it is the left subtree, which has height 1, right subtree कुछ नहीं है तो 0, right? Yeah, so Shamit, here is one reason why we have followed this convention, no? Uh,
Yes,
so
yes, I got it because I initially used to do with zeros, but now okay,
yeah,
fine. Mm.
yeah. Okay, all right. So now what will happen? Yeah, so 1 minus the slope of 5 is 1 minus 0, which is 1, right? Slopes I will mention. Yeah, okay, no, that might cause a confusion. Slope is +1, right? Because it is left, which is 1 minus 0. Now I add, let's say 3, right? So when I add 3, okay, Bipin is asking if only a single node is present, is slope 0. Yeah, what do you all think? So let's say initially I have only 5. What is the slope of 5?
0.
Okay, why is it 0? So remember, slope is the height of the left subtree. In
That's
this
right.
case, which is 0. Right subtree is 0, minus 0, which is 0. Okay, good. So now let's compute the heights and the slopes, right? So height of this is 1, height of this is 2, height of this is 3. Slope of this is 0. Okay. The slope of this is height of left subtree is 1 minus 0, so it's +1. Now slope of this is height of left subtree is +1. Oops, sorry. Uh, sorry, +1, and then uh, height of this is, yeah, sorry, 1 plus 1, which is 2. Sorry, I got confused. So this is 0. Sorry, the height is 1, right? This case height is 2. Here the height is 3, right? Now what is the left height? Left height is 1. 1 minus 0 is plus 1, right? And what is the height of this now? Can anyone tell me?
Height of which nodes?
Height of left subtree, which is 2, minus 0, which is plus 2, right? So now here you see, since the slope has become plus 2, there is an imbalance, right? So intuitively, what do you think we should do in order to somehow bring some balance?
It to the clockwise direction.
Right. In a way, what we can do is split the left subtree. Right. So what we can do is, in a way, since it is intuitively, since it's leaning towards the left, we can try to rotate it towards the right, right? So it's called a right rotation. What we do is, since this is causing the imbalance, we go to the child, right? And it's like you put 4 up, right? If you push 4 up, what will happen is 4 will come here. Whatever is on the left will remain as it is, but the 5 will come to the right, right? So is this understood? So this is known as a right rotation. Any doubts regarding this? Okay, on the other hand, the analogous one is if you have, 3, 4, 5. Again, if you see the height of this is 1,
Sir,
height of,
had one doubt.
yeah, go ahead.
While calculating the slope, basically it is the height of left subtree minus height of right subtree. So
Right.
while calculating the height of the left subtree, we won't consider the node 5. Because if we consider node 5, then the height for the left subtree would be 3, and here it would be 1. Basically, answer that of slope will be equal to 2.
No, we won't consider 5. The left subtree is starting from here, right? So actually we will look at the height of 4, which
Okay.
is 2.
So in turn, it's that if we are calculating the slope of node 5, then that node won't be considered, and
Yeah.
other nodes will be considered.
Right.
Okay. Thank you, sir.
Yeah. All right. Right. The same analogous thing for this also, right? 3, 4, 5. Okay, let me come down. So if we have 3 followed by 4 followed by 5, right? So what we'll do is we calculate the heights, which is in this case is 1, it's 2, this is 3. Then we calculate the slopes. In this case, it is 0. In this case, it is the height of the left subtree, which is 0, minus height of the right subtree, which is 1. 0 minus 1 is minus 1. And 3 left minus right. Left is 0, right is 0, 2. So 0 minus 2 is minus 2. So here we see that there is an imbalance, right? Analogously, like how we did for the previous example, here we need to do a left rotation, right? So again, we push 4 up, right? And whatever is to the right of 4 remains as it is, right? and whatever was above 4, right, it will come to the left of. Right, I hope you all are getting an idea of how it's happening, right? Any doubts regarding these simple rotations? So this is how you do a left rotation. If if so, what does this -2 indicate? -2 indicates that somewhere below, my tree is tending or imbalanced towards the right? And so I need to do a left rotation to balance out that right imbalance. Similar way for the left rotation, right rotation. Any doubt regarding this? Okay, Nagarajan is asking, what if 4 has a subtree? Okay, that's a good question. So you are asking what will happen over here, right? Right, so let's construct another example because this might not work. Yeah, okay. I'll answer that. Okay. Any reason why this won't work here? Yeah, it can. What value should I put here, for example? Can anyone tell some value which I can put here? Okay, Nagarajan is saying 1.
So
Can I
maybe
put 1 here?
3.5.
No, sir. One can't be there.
Okay, why can't 1 not be there?
So because it is smaller than 3, so it won't be on the right side of 3. So it won't come to 4 only.
Right. So
3.5.
remember, yes. So remember what, so just imagine if we are going about inserting 1, right? So we'll start from the root and we realize that 1 is less than 3. So immediately, 1 will always occur on the left side of 3, right? Wherever that is. So 1 cannot appear on the right of 3, right? Yeah. Although it is less than 4, but remember it is to the right of 3, so it has to be less than 3. Sorry, it has to be greater than 3. Whatever is to the right of 3 should be greater than 3. So as some of you mentioned, 3.5 can be, and 3.5 can be a valid number over here. Right. So if it's 3.5, then again, uh, yeah. So again, the height,
The slope of 2 will change to 0, but slope of 3 remains same.
So let's recalculate the slopes, right? So in this case, the slopes are, yeah, so this will be the height of this one left subtree. Now the height is actually 1, right? 1 minus 1. So since we added one node here, the height of the left subtree is actually 1 minus the height of the right subtree. So this -1 becomes 0, right? But remember the height is still 2, right? And so this still remains -2, right? Right? Any doubts regarding that? Okay. So now when we do so since it is -2, we have to do a left rotation. So again, we pull this 4 up, right? Right. So now the right subtree, right? This part, no change will happen, right? Right. And now what will happen when we push this up? this 3 will come here, right? And remember, 3.5 was to the left of 3.5 or whatever is here, that is to the left of 4. It should continue to remain to the left of 4. But remember, it was towards the right of 3. So hence it will, whatever is below this, it will just be towards the right of 3. Whatever is, there might be a big subtree over here. Oops, sorry. Right? But whatever it is, it will continue to be towards the right of 3. Now, do you think this is balanced? So
Yes.
height is 1, this case height is 2, height is 1, height is 3. Slopes, if you see, 0, -1, -1. This is 0. Yeah. Left is -1, -0 is -1. It's balanced, right? So basic rotation, I hope all of you have understood. Are there any doubts?
Sir, every rotation, I can find only one type of graph. There is no second possibilities there.
Hmm.
Initially, I thought ki 4 to 5 in the right hand side, then 4 to 3.5 in the left of 4, and 3 will be the left of 3.5. That possibility is ruled out.
Yeah, because then again, I
It
guess
will be
again it will
unbalanced.
imbalance. Correct.
Uh,
Yeah.
that
Yeah.
is why whatever its original graph left and right, that I should maintain. Then
Correct.
only this rotation comes to the balance. Okay.
Okay.
Mhm.
All right. But as you will see in the lectures, there are, luckily in this case, after one rotation, we reached a perfect balance, right? But in some cases, as we'll see now, there can be the case that, even after doing one rotation, there can be some imbalance, right? So let's just go through this example only. Let's see. Um, let's see if we can do something. Let's look at some visualizations. Okay. Uh, yeah. So similar to this, yeah. Yeah, why don't we try this example itself now? 5, move this up. I hope this is visible.
Yeah.
Okay. So now when I insert 4, so remember this 1 is the height. Okay. Since it is lesser than 5, it will go to the left, right? And we update the height of the root to 2. 3, okay. We saw that there will be so it will insert it to the root, and now it will recursively go and update the heights, right? And you see that there is an imbalance. And because of that, so the imbalance is at this node, right? We saw that this is +2. The slope of this is +2. So we will do a right rotation on 2, right? Okay, I hope this is clear. So yeah, let's try another example where things are a little more complicated, okay? So I'm inserting 6, 3. Okay, I'm just 6, 3, 7. Let's say we insert 2. Okay, till now things are looking okay. Now if I, okay, now I'm going to insert 4. Okay. Do you think the tree will be balanced or imbalanced after I insert 4? Think about it. Uh, Answer yes or no in the chat. Will it be imbalanced? Okay, one yes, one no. What do you think? Will it be imbalanced? Balanced, balanced. Okay, I think some you all might get confused. Right? Balanced or imbalanced? Balanced or imbalanced? Okay, imbalance, balance. I'm getting a balance of balance and imbalance. Balance. Okay. Let's think now where it will come. Uh, let's see. Okay, I insert 4. I'm going to insert 4. Yeah, so 4 is less than 6, so it will go towards the left. Again, 4 is greater than 3, so it will go towards the right. Okay, I reach the root. Sorry, I reach the leaf. Now I have to update the heights, right? I have to unwind the recursion, keep on updating the heights. Okay. So is it balanced or imbalanced? It's balanced, right? Because we none of the slopes are going to +2 or -2. Okay, I hope it's clear. All right. Now I'm going to add 5. Again, the same question. After I insert 5, will the tree be balanced or imbalanced? I'm going to insert 5. Imbalanced. One of you has said balanced. Okay, let's see what's happening. So you all know where it will come, right? It will come to the right of, oops, what a, oh, hmm. So it will come to the right of 4, right? Okay, we go down, we go down, we go down. Okay, now when we update the heights, we see that this becomes 2, this becomes 3, this becomes 4. Now, can you tell me which of the following nodes is having the imbalance? Which node has the imbalance? I mean, is it 6, 3, 7, 2, 4, or 5? Which node is having the imbalance? All right. I think most of you have got it now. It's 6, right? And what is the slope? What is the slope of 6? Faiz is confused. Okay, so if you see the slope of 6 is nothing but the height of the left subtree, which is height is 1, 2, 3. This is the maximum height, right? 3 minus height of the left subtree, which is 1, right? 3 minus 1, which is 2, which is plus 2, right? Higher slopes you should always refer to as plus 2 or minus 2. Yeah, include the plus or the minus. So that means that there is it is leaning towards the left, right? It is imbalanced towards the left. So we need to do a balancing. So we need to do a rotation to the right. So Faiz is asking, oh, the parent of 3 and 1. 3 and 7. Yes, yes, the parent of 3 and 7, which is 6, correct. Okay. Okay. So what can we do here? Okay, let's try to draw this. No, I won't. Let's see what is happening here. Okay, so we have 6, 3, 7. Then we had 2 over here, 4 over here. We saw that till here it was, yeah. And adding this 5 is causing an imbalance, right? And let's see the slopes. The slopes here it's 0, here it's, sorry, yeah, the height is 0 minus 1, which is minus 1. Slope is 0. Left subtree is 1 minus 2, which is minus 1. And slope here is 0, 1, 2, 3. 3 minus 1, which is plus 2, right? Okay, this is what we got. So what we might think is, okay, let's do a right rotation and it might work, right? Right. So if we were to do that, so what will happen? We go to the, yeah, if we go to 3, right? And we
Excuse me,
rotate
sir.
it. Yeah, go ahead.
Sir, by 6 node, how it is height, how it is slope is 2. Its slope is 2. I'm not
Yeah.
getting that.
Okay. So the slope is nothing but the height of the left subtree. Okay. So in that case, the height of this minus the height of this, right? That's clear, right?
Oh, okay, okay, sir.
So
I
the
was
height of
calculating
this,
the slope of the left subtree and right subtree.
yeah, that yeah, many a times even I get that confusion. But remember, the slope is always the height. So height is nothing but, uh, if you see the height of this subtree is nothing but the height of, yeah, so it is this, right? 2, 2 plus 1, which is 3. And of this is it's 2. So 3 minus 1 is plus 2, right? Yeah. So
Okay,
in
sir.
such case, yeah. So in such cases, if you see, uh, there is a plus 2 followed by a minus 1. Okay. So you can see that it is rotate, it is leaning towards the left, right? But then the node below that is leaning towards the right. Okay. So what you will observe is that a single rotation might not work, right? So in this case, if you rotate, let's say, one way to think about it is, uh, rotate from 3, rotate towards the right, right? So in that case, this will be 3, 2, right? 6 and 7 will remain as it is, right? And this subtree, right? This subtree tool will be towards the left of 6, which is 4 and 5. But do you think this is balanced?
No.
Right? It is not. Right? It is not in. It is, there is an imbalance, right? So in such cases, when there is a plus followed by a minus or a minus followed by a plus, right? What that means is that a single rotation, it won't work. So what you will have to do is you will have to do, oops, you will have to do 2 rotations, right? And how you do that is, yeah. So how you do that is, you first, first you rotate, you focus on this node and you rotate, since this is -1, you rotate towards the left. So you do a left rotation here, followed by a right rotation here. Okay. Okay. So think about it again. You do since this is -1, somehow I need to make this a little more balanced towards the left, so that when I balance towards the right, it will be okay. Right. So what we'll do is we will take 4, right? The node below that, and rotate it towards the left. So this 4, yeah, 5 will remain as it is, but this will come down, which is 3 and 2, and this is 6 followed by 7, right? And still this is imbalanced, right? And what we now do is, now we do a right rotation on 4, right? So in that case, it will be 4 will come to the top, followed by, yeah, we're doing a right rotation, so this will be 6. So this will come as it is, 6 and 7, followed by 5 to the left of 6, and this as it is. Is it? Yeah. Initially, it might seem confusing,
But
right?
sir, one
What?
question is there, sir.
Yeah, yeah, go ahead.
Uh, Suppose now you are looking this and doing this, right? Because you are
Looking this.
seeing this in picture, and you are,
Hmm,
you internally see ki I go left and then go right, then it will easy. But when I nail it down to this thing in the program, I have to give some logic. So when a
hmm,
node is not imbalance, say
hmm,
you are rotating a right rotation,
hmm,
knowing that ki that is that node 3 is not the condition of the, I mean the slope is not outside the boundary.
right,
How do you means do this when you write a program?
right, right. Yeah, that is a good question, no? So one thing which we need to make sure is that just by looking whether if it's positive +2 or -2, we cannot blindly do a left or a right rotation, right? So so what can an algorithm be for this, for doing rotation? Once we look at the node, right? If it is +2 or -2, right? We have to look at its children also, right? So since it is +2, we know we have to rotate towards the right. So we look at its left node. And then we see that if it's 0 or 1, right, we know it is +1, we know it's leaning towards the left. So a right rotation will not cause any issue, right? So then we can do a simple rotation. So the algorithm is look at the node which has +2 or -2. If it's +2, look at its left child. If it's -2, look at its right child. Look at the slope of the child. If the slope is of a different symbol, or if the sign is different from the node, if it's plus, if this is plus and this is minus, or if this is minus and this is plus, then we know that we need to do two rotation. Then we take this part of the tree and do a right and do a left rotation on 3. Right? Then we just call the rotation function again, right? We just call it once more, considering this tree, considering this as the node. And then whatever we do, whatever new tree we get, we again take that same node and rotate it towards the right.
I have just one thought over here.
Yeah.
Since this tree gets imbalanced by adding the node 5, right? Till such time, means till if we do not add the node 5, tree is balanced.
Yes.
So tree get imbalanced when you add the node 5. So what is the path from the root to the 5? In which path it get imbalanced? It is the 6, 3, 4, 5, right? In this direction.
Yeah.
So why that means I have to consider the rotation in the node of 6, 3, 4. This is the cluster that I need to rotate. And as you said, it is the +2 and -1. If this is the condition, why should I consider this as a two rotation? If this is the scenario, I directly swap the value of 4 with 6. In one rotation, I can get this thing.
In one rotation, you can.
I am
4
rotating
with.
right, but I will move the node 4 to the node 6 in that position, because ultimately you are doing that.
Yeah, I got it. Yeah. Okay. So you mean this one, right? This part you're saying, right? But the structure is also changing, no?
The four, then that principle will follow. Whichever is left of left, right of right in the original, that I will follow. If you just push this node 4 to in place of 6, then I think you will once again get the same structure that you have written in the right bottom.
Okay, let me see. So it will be 2. You're saying this should be 6?
No. You are moving that 4, na? So for 6 will come right of the 4.
No, sorry. So I thought you meant we are not swapping 6 and 4.
No, you are basically, what we are doing, we are bringing this 4 in between 3 and 6, so that entire thing, this 6 and 7 clade comes to the right hand side of the 4.
Yeah, got it. So you are directly somehow trying to join these two.
if you if you think this is a structure, if I break the line between 3 and 6 and put something and that becomes the pivot point, then your graph get balanced.
Then you will get something like this, right?
Yes, then I will something get this 432 and another side is 4675, because
Yeah,
I'll
yeah, but then, yeah, yeah, but how do you decide that you need to break it here, or you need to add something here?
that is the logic that you are given, because I know my direction of imbalance is 6345 in this route.
Hmm,
So anyway, any rotation I will consider the top three node only in the path of the direction it get imbalanced.
hmm,
So
hmm, hmm,
my operation zone is 634. Now I will check this logic what you said ki it
hmm,
is +2 and immediately that is -1. If it
hmm,
is +2 -1 in this way, then I will swap, means do this perform, means bring this 4 to up, or else I will do the 3 to the top. If I do this, say if 3 is 1 or 0, then I
hmm,
will bring 3 to the top and do the balance. And since 3 is -1 slope, so I
hmm.
will bring 4 in between 3 and 6 and I will balance. This what I am saying, sir.
Got it, got it. Okay, okay. Yeah, I think that might work, but I'll have to. Yeah, will it work for all cases? Will this conditions work for all cases? We'll have to check. No? So I'm getting the point. What you're saying is look for the path which is causing the imbalance, and so since so look at each path, and since here that is happening, uh, yeah, bring 4 on top so that you'll get something like this, and then do a rotation, right?
Yeah,
Hello?
yeah, sir. Yeah, that's what I am
Yeah,
saying.
yeah, yeah, yeah. I think that will, I think it should be okay, but I'm not very sure. Like we have to consider all cases, whether it will work and all of that. Okay. So others, what do you think? Confused? Yes, no, this double rotations.
Sir, actually, I'm still confused about how to get the node about which we have to rotate.
Hmm. Okay. So you understood that these are the slopes. The ones in the boxes
Yes,
are
sir.
the slopes. That is clear, right?
Yes, sir, clear.
Ashutosh, yeah. So uh, now now we have to just concentrate on the node which has +2 or -2, because that node there is an imbalance. Okay. So in this case, which node should we focus on?
So 6 have +2.
Yeah. So maybe let me take a simpler example first. So 6, 3, 2, right? In this case, again 6 has an imbalance because uh, the slope is +2, right? Okay. So we need to do a rotation, right? And the way to do that is look at so in this case, since it's plus, means it is leaning towards the left. And since it is leaning towards the left, we need to do a rotation towards the right to balance it. Is that much clear?
Yes, sir.
Mhm. So what we need to do is somehow we need to push this tree structure towards the right. So one way to think about it is, we put a balance or we put a beam or something over here. Sorry, not a beam. Somehow we try to pull tree up, right? Why do we try to pull 3 up? So that 6 will move towards the right and the entire structure will move towards the right, right? So we look at the node, we look at the child of the node which has an imbalance. Is that clear?
Okay, sir. Means we have to find which node is have long roots, right?
A long path, yeah. Or path as in long as in its slope should either be +2 or -2. Yeah,
But sir, in this case, the slope is not +2 or -12. The slope of 3. But we have
What
to
is the
choose.
slope of 3?
The slope of 3 should be 1.
+1.
Yeah.
Correct? Yeah. You're right. So we are doing the rotation. We have realized that 6 this node 6 has an imbalance. Its slope is +2, right? So we will do a rotation on 6, right? A right rotation on 6, which means that we'll have to look at the child of that node to do the rotation.
And similarly, sir, if there is another imbalance, then we have to see the imbalancing node, right? Imbalancing side of the node, right?
Exactly. Exactly. Yeah. So in this case, if you see, yeah, we have to push this thing up. So this will actually be 3, and the left of that will remain as it is, right? And this will move towards the right. So we get a balance now.
Understood. Thank you.
Okay. Okay, so for this left and right thing, I would say you all try to do it manually. If it is both, if both are plus and plus, it's very easy. You have to just do 2 rotations. But when it is plus and minus or minus and plus, right? That is where you need to do first one type of rotation and then the other type of rotation. So what we did first here is since this is -1, we do a left rotation at this point. So we bring 4 up and then we reorganize. The right will remain as it is and we reorganize this. And then we do a right rotation on 4 and we get this structure. Okay, so actually this visual, so this is the same thing as this. If you see 6, 3, 7, 2, 4, 5, 6, 3, 7, 2, 4, 5. But this doesn't show the exact rotation. What it says is we need to do this rotation and it automatically somehow does it. Yeah. So if they had shown that a little more better, it would have been good. It's the same thing which we are getting. All right. So this was regarding AVL trees, balancing it, uh, left rotation, right rotation, right? I hope that is clear. Any doubts?
Hmm.
Okay. So, okay, now I think we can move on to another concept, which is Huffman codes. How many of you all know what is Huffman codes? Yes, if you know, and no, if you don't. No, I think majority is no. Okay. All right. So, okay. So what should I do? I'm just thinking what to do. Shamit, do you want to explain what Huffman codes are?
No, sir, but not in that much confidence. I can explain that.
Okay. All
Uh,
right.
in,
Yeah.
in
Yeah.
short,
Yeah.
I can tell means it's when you are sending some communication, you this Hopman coding basically reduce the file size and able to send you the same communication uh, to the receiver end with a lesser cost. So, in a very since general way, suppose you are sending some message to the one point to another point. If you send it directly, it will take the size as per the ASCII values. But with something I am doing, I am able to communicate the same thing, but with a lesser file size. So what we are doing inside that to send the thing in the lesser file size, it's the comes to the Hoffman coding part, some mechanism that the Hoffman coding. It will, and then the Hoffman coding this is the general thing. And what its Hoffman coding is doing, it will identify uh, means means the frequency of the letter in a paragraph, and try to means allocate some code to that frequency or the probability of that particular letter in the paragraph, and then it will generate some code and dispatch that.
All right. Yeah. Good attempt, Shamit. So,
If I take some example, then I think it will be a little clear. Suppose you take, I want to send a communication as A, B, B, C, D, A, B. Suppose this thing I want to send it. Now, if I want to send this communication without doing anything, so each letter 1, 2, 3, 4, 5, 6, 7, 8. So 8 into 8, 64 bits, right?
why 8 bits for one letter?
ASCII values are 8 bits, right? For A.
Okay. 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 So I hope everyone knows what ASCII is. Or let's take a simpler example. No, let's say we have only A to Z, right, which is 26 letters,
Hmm.
right? So how many bits are required to encode all the letters from A to Z? Can you respond on the chat, others? How many bits? Let's say I want to just send A to Z. How many bits are needed? Uh, okay, so remember that all communication happens through zeros and ones, right? So, for example, A will have a bit some zeros followed by one something. B will have some other combination. C will have some other combination. D will have some other combination. So my question is, how many bits do you think are needed, for each letter? Someone is saying 26. Others confused, not sure. Okay. Someone is saying log 26 to the base 2. Someone else is saying not sure. 2 to the power 5. Okay. Yeah. Yeah. Sorry. Pras R. Sorry, I don't know your name. Yeah, can you explain why you said log 26 to the base 2?
Sir, we need the number of digits in the binary representation of 26. So it is log 2.
Okay, okay. And someone responded with 2 to the power 5. Arya, yeah. Can you tell me why 2 to the power 5? Arya, are you there? Yeah, I understood. 2 to the power 5 is 32. I understood. 2 to the power 5 is 32, but so do we need 32 bits? Okay, okay. So what, yeah. So so the thing is, see, remember that each bit, right, you can represent, let's say we had only one bit, right? So we can represent how many alphabets, for example? Only two, right? 0 or 1. So if we had, let's say, 2 bits, we can represent 00, 01, 10, 11. So this can be A, this can be B, this can be C, this can be D. But that's it. We can just represent 4, right? Which is nothing but 2 to the power 2, right? So with the number of bits that we have, we can represent 2 raised to that many bits, right? We can represent that many letters, right? So what someone said about log 26 to the base 2 is exactly that, right? So log 26, we can consider 26 as 2 to the power less than 2 to the power 5, right? 2 to the power 5 is 32. So what that means is with 5 bits, if we had 5 bits, 1, 2, 3, 4, 5, we can represent 32 alphabets or 32 characters, 32 distinct characters, right? So if we had messages which had, let's say, A to Z, we can represent it using 5 bits, let's say. Okay, Shamit, go ahead. Yeah, I just wanted to clarify that. Yeah.
Oh, fine, sir. I just wanted to come there only. So you said that because 2 to the 5 power 5 is the maximum. That is why I write 2 to the power 4 to 5. In some part, I don't need that. So that why should I send the additional thing? That is why it will may if you use A to Z all the character, it will vary from 2 to the power 4 to 2 to the power 5.
Yes, yes. Yeah, that is clear. No. Now, how is Huffman coding used? Or we can just send 5 bits, right? Why do we need
Yes,
uh,
yes, yes. Yeah.
yeah. So you are giving this example. You can go ahead. Yeah, you
No,
can
I think,
explain.
sir, you explain that one better, sir, because there might be first time listener is there, so it will be good for if they heard from you.
No,
I
okay,
may
nothing like
mistake in here and there.
okay. No issues, no issues. So actually, the sir has explained it well in the lecture. So maybe I'll take that. Uh, yeah, right. Huffman coding. So yeah. So all of this is there in the lectures, right? What we just discussed now. So um, yeah. So what we need to see is that traditionally we might need, uh, 2 to the power 5, 5 or 4 bits, right? But what happens is many a times what we can do is, so if a message set has only, let's say, a few letters, or there are some letters which are occurring more frequently, then instead of using all the 4 or 5 bits, right? The logic is, if there are letters which are occurring more frequently, okay, the question is, if there are letters which are occurring more frequently, let's say vowels, A or E or I or whatever, should that have a shorter length or a longer length? Let's say we are allowed to vary, the lengths of each character. So for example, oops, sorry. So for example, I can set the value of A as 1. I can set the value of B as 111. Okay, I can give whatever I want, but it should be consistent. So more frequently occurring letters, should they have shorter lengths or longer lengths? What do you think? Can you type on the chat? Frequently occurring letters should have shorter lengths or longer lengths? Right? It makes sense to, yeah, most three of you have said shorter. Makes sense to have it shorter, right? So in this example itself, if you consider A is occurring 1, 2, 3 times, right? And maybe it's occurring even more number of times. So the letters which occur more frequently, if we give it shorter codes, right, the overall length of the message will also reduce, right? And that is the key idea in Huffman coding, right? We look at letters which are occurring more frequently, assign shorter codes to them, and letters which are occurring least frequently, we assign slightly longer codes to, right? So, and another thing to notice is that, another thing to keep in mind is that each of these letters, right? So remember that you're sending these, you're communicating as a series of zeros and ones, right? So you really don't know. So let's say this is a string of bits, right? So you should be when at the receiver's end, when someone gets this, they should also be able to decode it quickly, right? Decode it correctly, right? So in this case, we know when we start from left to right, we know that 001 is C, right? But let's assume in this case that D, instead of 10, it was 0010. Okay. Now, on the receiver's end, if I go from left to right, I see 001. Okay. Then I see it is C. But then I notice that there is another 0 here. Okay. So does it actually mean C, and is this the start of the next character, or does it actually mean D? That is not clear, right? So the encoding, or how you translate each of these characters to bits, it should be in a way that none of the characters are a prefix of any other character, right? That is an important property. Is that clear? Any doubts in that?
Oh,
Okay, so here also, if you see, uh, A A is 11, B is 01, C is 001, D is 10, and E is 000. All of them, are not a prefix. Any X is not a prefix of Y or vice versa, right? All of them are distinct, right? So the problem is how you can come up with this set of encoding for each letter based on their frequency, and it should be uh, 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 and it should any letter should not be a prefix of the other, right? So that is the basic thing of Huffman coding, right? So here you can see that it's 001 is C, right? Then we go to 000 is E, right? And 001 is C again, and 1 we know is A, and 01 is B. All right. Yeah. So yeah, I won't go into all these details. You can go into that. So what is actually happening is what we actually do is we look for each letter, we calculate the frequencies. Sorry, we calculate the frequency. It is like a percentage of the total number of, let's say there are 100 words in 100 letters in a paragraph. In that 100 letters, A appears 32 times, B appears 25 times, C appears 20 times, D appears 18 times, and E appears only 5 times. Right? So, uh, yeah. So once we have this, it makes sense for us to allocate the least number of bits for which of these alphabets? Right? For A, right? Because E is occurring only five times out of 100. So if we increase the length of E also, it shouldn't matter, right? Okay. So yeah, so all this you can, yeah,
Sir, can
look
you
at in the lecture.
sir, can you move to the previous slide?
Yeah.
So here C is occurring 20 times and D is occurring 18 times, right?
Hmm.
Then how the bits of C are more than D? You said most occurring items should be less bits, right?
Yeah. So I think this is not the final. This is just an example, I think. This is not the final or the most optimal number of codes. Okay, I think so. Let me check. So this was just an example which sir gave. We'll go to the optimal thing later on. Suppose we have the following frequencies. So suppose we have, and this is one such possible encoding, right? This is not the most optimal one. Yeah. Yeah. So what Huffman coding does is, right, uh, it tries to create a binary tree. Okay. So what it does is, and the letters are at the leaves. Okay. And how we do this, how we construct this is, yeah, I'll come to that. So yeah, I'll skip all of this. Yeah. So what we actually do is we have these frequencies, right? Now what we do is at each step, right, we choose the uh, letters with the minimum frequency. Okay. So in this case, the minimum frequency is 18 and 5, right? So we choose both and we combine them together, which is DE, right? So now DE becomes a new letter or new, yeah, you can say a new entity. And we add up the frequencies of D and E to get this, right? Now again, we do the same thing. So this is why Huffman's algorithm is a greedy algorithm, right? At each step, you just locally check for which are the two least, the two nodes with the least frequency, right? So here it is 0.2 and 0.23. So you combine both of them and you get it as CD, and you add both of them, right? And now again, now you see that these two are the A and B are the least, the least, right, amongst the lot. So then now we combine A and B, right? What happened? Right. We combine A and B, right? And finally, yeah, and we continue this process until we get only 2 nodes, right? And what we do now is, now that we have got only 2 nodes, we go back and construct this entire tree, right? What we do is, so the base case is we have only 2 letters, in this case A, B, C, D. Now we build a tree by putting both of these at the as the leaf, right? And then we go back, right? Remember now what we had done is we had combined A and B together. So now we split A and B, right? And if you look at this step, we had combined C and DE. Now we split C, D, and E, right? Then we had combined D and E. So we split D and E. Is this part clear? So notice what we did. We noticed that D and E are occurring the least frequently, right? So in a way, it makes sense for us to keep them at the bottom of the tree. Okay, I didn't explain why at the bottom. Now what we do is, since it's a binary tree, what we will do is simply label each of these as 0, 1, 0, 1, 0, 1, 0, 1, or 1, 0, right? Anyhow, anything doesn't matter. So the code for A now becomes, you start from the root all the way down, which is 0, 0. B becomes 0, 1. Can you tell me what C is? What is the code for C, D, and E?
10.
C is 1, 0. D is
110
1, 1, 0. E is
and E is 111. 111.
right. So notice what we did here. Now, so since D and E are at the bottom, right, at the leaves, right, and at a grade, so, and they are the ones which are occurring the least frequently, right? So in a way, we are pushing them to the bottom of the tree. The ones which occur more frequently are slightly towards the top, right? And this tree-like structure ensures that each of them, the prefixes of one does not match any of the other. Okay. So is this clear? Okay, so the example which Amit gave, no? Let's take this example only, na? A, B, B, C, D, A, B, right? Let's look at one visualization. A, B, B, C, D, A, B. A, B, B, C, D, A, B. Right? So here you can see that, okay, let me add a few more B's, right? So here you can see that B is occurring the most number of times. A is occurring, B is occurring 1, 2, 3, 4, 5, 6, 7 times. A is occurring 3 times. C and D are occurring just once, right? So in this case, which letter should have the shortest length? Right? B should have the shortest length, right? Okay. So let's see how Huffman coding does this. So when we try to build the tree, we need, okay, I hope this is visible. Yeah. Initially, yeah, we count the frequencies and we take the ones which have the minimum frequency first, right? And yeah, which is C and D, right? And we merge them together, right? And the frequency of that is 2, right? 1 plus 1, which is 2. Then we look at, we compare this with the next, so now we have 3 elements, which is A, B, and C, D, with frequencies 3, 7, and 2. Now we again choose the next 2 minimum, right? So which is nothing but A and CD, right? Which is A and CD. We combine them together, right? A and CD to get 5, right? And now only 2 are left, right? 5 and 7. So we combine them together to get 12, right? So don't worry about these numbers, right? It's yeah. So what you need to check is, yeah, and so this constructed the tree and merged it together. So you can do it separately also, right? And so now A will actually be 0, 1. B will be, can you tell me what is the value of B? What do you think is the value of B?
B will be 1,
B will be 1.
A will be 0, 0.
A will be 0, 0.
Then your C will be 0, 1, 0.
Hmm.
And D will be 0, 1, 1.
0, 1, 1, right? And notice that B, since it's occurring 7 times, we have, it just has a single bit, right? Yeah. Yeah. So this is Huffman coding in general. Yeah. So yeah. So any doubts regarding this?
Sir, here the 1 0 coding part, then we can interchange the left and right child, right? Means 0 to 1, 1 to
Exactly.
0.
Exactly. It won't make a difference, right? It's just another type of encoding. Yeah. So in that case, this will be B will be 0 and A will be say 1, 1 or whatever. 1, 1. Yeah. Yeah. All right.
Sir,
Yeah.
In Hoffman coding, we are sending the message from one point to another point. The idea is to compress that and send it for the lesser cost, right?
Yes.
So, but in the general normal, when we use some text or paragraph, there is not only the 26 alphabet is there, but apart from that alphabet, some other things is also there, right? Many of the special character, there is 0 to 9, all these things. If you add those, then it will go beyond, means this thing, 2 to the power 5, what we are using. On that time, what you will do?
Yeah, the same thing, no? Like,
Then you are increasing that 2 to the power 6, 7, right? Like that.
yeah, exactly. Yeah.
Oh, that's such.
You see, even if you were talking about ASCII also, right?
Mm-hmm.
ASCII, you have 8 bits, right?
Hmm.
8 bits to refer to it. So which is 2 to the power 8 is how much?
256.
256, right? So you can represent 256 characters using ASCII, right?
Hmm.
But do all these 256 characters have the same frequency? No, right? many of them we use it very rarely, right? So in compression algorithms and all, what can be done is uh, uh, instead of using 8 bits, right, we can, based on the frequency of the character, uh, create Huffman codes, which will, considerably, maybe this 8 will reduce to maybe 6, for example. I don't know. That we'll have to see. Yeah.
Okay. But this coding means B is equal to 1 or A is equal to 00 or 01. That will automatically, this algorithm will decide what should be its binary code, right?
Yes, yes. Correct, correct. Yeah.
Okay.
Right. So, yeah, so so today we talked about two things, right? This AVL trees and the Huffman coding. So I would say for those of you, like what you all can do is go through the lectures once quickly, but more implement this Huffman coding, right? It doesn't look like a very difficult thing, right?
So if you can discuss that job scheduling part in
Which one?
the scheduling part, sir.
The job scheduling one is this one, I guess. Minimizing lateness.
Yes, sir.
All right. Yeah, you had any specific doubt in this?
No, overall not. Means if you discuss, then things will come, sir, because I've gone through once, but not.
Yeah, yeah. Okay. So no, I'm just thinking in interest of time. Yeah, I can go through it quickly. This one only, right? Minimizing lateness.
Okay, yes, yes, yes.
Yeah, yeah. So quickly, I'll just go through it. So this is another type of greedy algorithm where the context is, yeah. So IIT Madras has a single 3D printer and a number of users need to use this printer, right? And for each of the user, it takes some time to print, right? Now, what we have to do is to and each of the users has a deadline, right? So, for example, so let's say there are 1, 2, 3, 4 users. Each of them take, let's say, 2 2 minutes. This takes 4 minutes, 8 minutes, 6 minutes, and they have deadlines. Let's say the first task takes, I have to finish it within, let's say, 5 minutes. Two has to finish within, let's say, 10 minutes. Three has to finish within, say, in 8 minutes. And four has to finish within 3 minutes. No, sorry, not three, sorry. Let's keep a higher deadline, 15. Hmm? So you have tasks, each of them takes some time t, and each of them. Oh, okay. So each user will get access to the printer, but may not finish before the deadline, right? So so the thing is, I need to create a schedule, right? So a schedule can be, let's say, uh, can you all tell me one schedule, any one schedule? A possible schedule. Mm, Snehal, can you tell me a possible schedule? Snehal, are you there? Yeah, Faiz, can you tell me a possible schedule? Okay, I guess people are not listening.
So the confusion part is, sir, so where I get actually confused, ki, I can start with say job one means 1, 2, 3, 4. These four job you have given.
Mhm.
So I will mark it as J1, J2, J3, J4, right?
Mhm.
So what I can do, first I will complete the J1,
Okay,
then I will
let's see.
complete the J2,
Okay, so
then
let's
I
say let's take J1 takes
2 minutes, then I will complete J2,
J2. Okay, J2 will take
6,
6, right?
then I will complete J4,
J4 is
6
6
plus 6,
plus
12.
6.
So within this 15,
Okay, and
right?
then I'll complete 3.
No, 3 I cannot, because 3 the time you have given deadline is 8. So within that I cannot.
Yeah. But see, the criteria is you have to finish all 4 jobs or whatever jobs are given.
Then
The cri- the criteria. Okay, good. So the criteria is you have to finish all the 4 jobs, right? Now, in this case, let's calculate the lateness. Okay, let's call it as it finished. It finished in 2 minutes. But what was the deadline?
5.
5. So if it finishes within the deadline, we'll say it's not late and we'll give it a value 0.
Oh, okay. I got it now. Okay. Because you are calculate the total lateness and you are minimize that. Idea
Yeah,
is that. Oh,
yeah.
acha, acha, acha.
So for others also, I'll just quickly explain. Did you all understand how I got this number line? Any doubts there? Okay, it's simply that this is the time. So time t is equal to 0 minutes. Let's say I started job 1. Okay, job 1 takes 2 minutes, right? So from 0 to 2, I finished 1. Then I decide to take 2. 2 takes time 4 minutes. So from 2, I go 4 minutes, I finish 2, right? And I end at 6. Now, next I choose, say, job 4, and job 4 takes 6 minutes, right? And so 6 plus 6 is 12, right? And then just a moment. Are you able to hear me?
Yes.
Okay, sorry. Yeah. And and then finally you take job 3, which takes 8 minutes. So from 12th minute, you go till the 20th minute and you finish job 3. Now, the algorithm is you want to, okay, now let's see how late we are based on the deadlines, right? So job 1 is, let's say we finished in uh, well within the deadline, right? We finished it at 2 minutes. Deadline was within 5 minutes. Great. So if it finishes before the deadline, then the lateness is 0, right? We won't consider negative values. Now, the lateness of 2, or how late are we for with respect to task 2? Uh, uh, we had to finish 2 by 10 minutes, right? 2 also we are quite good, right? We finish it within time. And 4, we see that lateness of 4 is, yeah, we have to finish within 15 and we are well within time, right? So we finished, this is also 0. Now L3, we realize that we have to finish it within 8, right? But we finished L3 only in the 20th minute. So the lateness is actually 20 when we actually finished minus the deadline, which is equal to 12, right? So if we consider this schedule, no, 1, 2, 4, 3, the lateness is actually the max of all of this, right? Which is nothing but 12. All right. So I think in the practice assignment, instead of max, I think you have to take the sum of all this lateness. And what you have to do is somehow you have to minimize this maximum, right? So if I take some other schedules, for example, 1, 2, 3, 4, can I reduce this from 12 to something else, right? So the question is, what is the algorithm which will give me a schedule which will minimize the lateness, right? Yeah. So in the lecture, sir has, can you all think of some strategies? What strategy should I use? Okay, so in the lecture, sir talks of different strategies. So once you go through it, you will understand. And the most optimum strategy is to choose the tasks in the order of their deadline.
Finish time.
Sorry, finish time, right?
Mhm.
So in the order of their finish time, when they finish first. Yeah, so deadline also seems like a very plausible thing to think about, right? But yeah, so in the lecture, sir talks about why that is the optimum way.
Yeah, but sir, here you won't give me any credit if I able to finish within before deadline. Suppose instead of means if I am late, say late by 12 units for the job 3, if you denote that as a -1, say -12
Yeah,
means it is negative, and whenever I have something before you give me a credit, then the
yeah.
algorithm will change, right? Maybe the strategy I need to take different, or the same strategy is applicable there.
So that's a variation of this algorithm. So I'm not sure. Uh, my sense is that this algorithm will work for the variations also.
Means whatever, whether you give me credit or not, always we consider from the finish time.
I think that is what sir argues also in this lecture uh, yeah, in terms of the correctness, no? Mm, it might change, I'm not sure, because since your for tasks which finish early, you are in a way changing the function, right? You are increasing or you're adding some things. So in a way, you want to look for.
So on that time, sir, I will see whatever is the late one, means wherever I score a negative, that will remain same because I am going out. But whatever is the positive side, that thing I can permanent perm, give a permit to inside then, so that the maximum I can gain the maximum based on the deadline and the finish time. in the same example, if you calculate, then I think you go back to the where you are calculating that thing.
Yeah, yeah, yeah. Let's try that. Yeah.
Yeah, if you just give the credit for the wherever, so it is 2, deadline is 5, so it is +3, L1 is +3,
Hmm.
and your L2 will be, it is 2 plus means 6, it is given
Plus
in
four, no?
+4, and your this thing is +3 again, L4 is +3.
Hmm.
So it is 3, 7, 10. So it is ultimately -2 if I follow this.
Correct, correct.
Is there any other thing which can give me less than? So only thing I can mm, permit in between job 1, job 2 and job 4. Right? If I shuffle this, say if I bring the job 4 first,
Hmm.
I will keep that job 3 in the last, because this 0 to 12 I will finish these 3 tasks, job 1, job 2 and job 4, but I can do 4 first, 1 second and 2
Hmm. Hmm.
last. This permutation is possible, because anyway at any combination I will finish at 12 only.
Correct, correct.
So that part I think we need to change, means check, and whether that is give the same result, then I can conclude kino this is the ultimate one.
Yeah, yeah. So I think that's a good exercise to check. Yeah. Put it on discourse, no? I think we
Okay,
can have a good discussion and see.
okay,
Hmm.
I'll put it in discourse. Okay.
Yeah, yeah. So even I don't know. Even I don't know whether it will change, because why I'm not sure is because if you see the claims which are made, uh, yeah, so here we are just thinking about the deadlines, right? The proof works for the deadlines, but we are not checking with respect to the finish times, right?
Hmm. Because you consider
So,
that as a zero.
yeah, yeah, yeah. So I guess, yeah, if you consider the finish times and the deadline, yeah, so so the lateness is definitely changing. So I'm not sure if, that strategy is the most optimal. Yeah, I'm not sure.
Yeah, I will
Yeah,
put it in Discord so that discussion can happen, sir. Okay.
sure, sure, sure. Good, good. Or I think it might be variations of this lateness algorithm is there online also. I haven't checked it, but a lot of variations are there, So I'm pretty sure the one which you also said will be there. Even I'll check it. I'll also see. Hmm. Okay. Okay, everyone. Yeah, so for week 7, I would say the algorithms are not very difficult compared to the previous weeks, right? Like you saw the Huffman coding, you saw this idle time lateness problem, but the algorithms themselves are not difficult. Uh, yeah, but for the ABL trees, and the Huffman coding, how do you actually code it, right? I think you should focus more on that. These two, right? The other two algorithms are very easy to implement, so that's not an issue. Yeah, but ABL trees and Huffman coding, right? Try to implement them on your own or and see how it works, right? Since you now have some idea about the concepts, right?
So what we have in week 8 onwards
Yeah, so
now.
week 8 onwards is divide and conquer and other type of. So this week you saw something about the greedy approach, right? Where you just make one local decision, one after the other, and globally, you get the optimal solution. Next week, you'll be looking at divide and conquer, where you divide a big problem into smaller parts. And then there is something called dynamic programming, where, like, unlike greedy, right? You go along a path, then you realize it's not optimal, then you backtrack or you come back, then go along another path. So backtracking, dynamic programming. So different types of algorithms or different classes of algorithms you'll see in the coming weeks. Okay, so let's stop here today. Okay, so I hope all of you got some understanding of AVL trees and Huffman coding. Yeah. All right. See you all. Okay. Bye. Good night. Bye.
Thank you, sir.